This is the first of 2 lessons on the Flight Management System, which is often abbreviated to FMS. This one is mainly on components and hardware, whilst the second concentrates on equipment operation. All modern airliners contain a flight management system. It combines various subsystems into one integrated system, designed to provide continuous automatic navigation, guidance and performance management. FMSs can vary considerably from manufacturer to manufacturer and type to type. The system architectures can be different, and different manufacturers often use different names for the same basic component. This makes it difficult to generalize about them, and the details of any particular system will be studied during your type conversion. However, they all contain the following basic subsystems. A flight management computer, or FMC. This is the central processor which combines all the other components into an integrated system. It also carries out the navigation, guidance and performance calculations. A control and display unit, or CDU, for each pilot. This allows them to input information through a keypad and receive information through a display screen. Our arrows therefore go both ways. 2 or possibly 3 inertial reference systems to provide position, altitude, acceleration and velocity information to the flight management computer. An air data computer, or ADC, to give altitude and airspeed information. There are radio navigation inputs, navigation and performance databases in order to provide route, navigation aids and basic aircraft data, and engine and fuel data. The pilots manage this system in order to generate commands to the flight guidance system. This is a generic term which can either mean the flight director display on the electronic flight instrument system, or can mean the autopilot. This is the layout of an early model of the FMS fitted to the Boeing 737-400, and although it did not have GPS, it was very similar to our basic model. You can see that there is one flight management computer serving both pilots and 2 inertial reference systems. However, here is a later model. The architecture looks more complicated because there are 2 flight management computers, 1 for each pilot, and 3 inertial reference systems. However, the basic components are the same, and the way the system works is the same. The commands generated to the flight guidance system give 2 types of guidance. The first is lateral navigation, or LNAV. This is in the horizontal plane, steering the aircraft left or right as required to follow a route through a series of waypoints to the destination. The second is vertical navigation, or VNAV. This is the vertical profile and takes account of the optimum flight level for the weight and distance, the fuel used and the diversion requirements. FMS lateral navigation is more comprehensive than the simple waypoint-to-waypoint navigation provided by a first-generation inertial navigation system. The greater computer power available in more modern systems allows a lateral flight plan to include the following: the takeoff runway, including an update of present position on takeoff, the standard instrument departure, or SID, the transition from the end of the SID to the en route flight level, waypoint steering en route, the transition from the top of descent to commencing the standard instrument arrival, the standard instrument arrival, or STAR, the selected instrument approach to the landing runway, a missed approach and go-around, if required, and a flight plan to an alternate airport. Vertical navigation is also complex, and there is a lot of interaction with lateral navigation. We will show some of these facilities by the use of examples. For instance, here is a section of a takeoff and climb profile. If there is a noise abatement procedure at an airport, an aircraft will be required to climb quickly to minimize noise at low level. To achieve this, the climb is carried out at takeoff safety speed plus 10 knots until past a specified waypoint. We will then assume that there is an air traffic control requirement to maintain 250 knots indicated airspeed until reaching 10,000 feet. We need to cross a radio facility called Alpha Bravo Charlie above 4,000 feet. The computer will have to compute whether, with our present thrust, our airspeed of 250 knots will give us the required rate of climb. Next, we must cross Bravo Charlie Delta at 6,000 feet. Above 10,000 feet, we continue with the climb at the aircraft's economical climb speed, which will vary with the weight and static air temperature, and which will be calculated by the computer and passed to the auto throttle. A climb power setting which reduces the N1 by 3% is often used in order to save engine wear. We will assume that, at this weight, this setting gives a climb speed of 302 knots IAS, converting to 0.597 Mach. This is the point at which the Mach number becomes more limiting than the IAS. At the top of the climb, the aircraft is commanded to level flight and is accelerated to the economical cruise speed. Again, this is calculated by the computer, taking into account weight, altitude, and temperature. As the aircraft proceeds along the level portion of the route, as fuel is burnt and the weight reduces and as the temperature changes, the optimum economical cruise speed is continuously updated. There may come a point along the route where the aircraft is now light enough to make it worthwhile continuing the cruise at a higher flight level, subject to air traffic constraints. This is called a step climb. The considerations for the descent are similar. A top of descent point is computed automatically. Speed, distance, and altitude constraints require continuous calculation of required thrust, right down to the final approach. A high-speed descent or a fuel economy descent may be selected. We'll now look at some of the components. The first of these is the Control and Display Unit, or CDU. This is the piece of equipment that allows the pilots to communicate with the FMC. It consists of a plasma display and a keypad. Let's start with the display. You can see that, about 3/4 of the way down, there is a horizontal dotted line. Above the line, we have the fields. These are specifically for data entry and are used in connection with the line select keys. Below the line, we have the scratch pad. As the name suggests, it is where we make draft entries and check them before we commit them into the computer. Suppose that we want to enter a gross weight of 61,700 kilograms at startup. We type in 61.7. We can now check it, and if there is a mistake, clear it and re-enter it. When we are satisfied that it is correct, we touch the line select key. The number jumps from the scratch pad to the field. However, the scratch pad also has a second use. The computer is programmed to pass relevant information to the pilot should it be necessary. These are called alert or advisory messages. Alert messages have the highest priority and they identify a condition which must be acknowledged and corrected by the crew before further FMC guided flight is advisable or even possible in some cases. Advisory messages have lower priority and inform the crew of the CDU entry errors or system status. Below the display is the keypad. There are number keys, letter keys, and function and mode keys to select particular pages or functions. There are also 4 indicator lights called annunciators. The first is the display light. The CDU is menu-driven and there are many different pages available. If the page that the crew have selected is not related to the active flight plan leg or the current operational performance mode, The display light reminds the crew that they are not using the optimum page. The fail light illuminates if any FMC failure is detected. The generation of any alert or advisory message causes the message light to illuminate. This will then draw the crew's attention to the scratch pad. Finally, there is a function in the FMS called offset. The aircraft can be programmed to fly parallel to, but a fixed distance from, the FMS programmed track. This could be used to avoid the turbulent wake of the aircraft ahead, for instance, or to increase separation from opposite direction traffic. Unfortunately, the display on the electronic flight instrument system does not make it obvious that the offset is being flown, so the offset light stays on to act as a reminder. The CDUs are used during pre-flight to manually initialize the IRS and FMC with dispatch information, flight plan routing, zero fuel weight, and planned cruise altitude. In flight, they are used to control the FMC and display flight information, and to show alert and advisory messages. There are two databases, one for navigation information and the other for performance information. The navigation database contains the position and, where required, the elevation and frequency of navigation aids, airports and runways. It also contains the operator's route structure, airways, waypoints, SIDs, stars and approach procedures. This information is subject to constant update, so the period of validity of any set of data is 28 days only. A new set is issued by the company supplying the data and is loaded into the flight management computer, usually from a form of compact disk. This can only be done by the maintenance personnel. Pilots cannot access the permanent navigation database. Two sets of navigation data must be carried, one for the current 28-day period and one for the following one. The 28-day period of validity is called an AIRAC cycle. Unless two sets of AIRAC cycle data are present and one of them is current, the FMS will not continue with its startup sequence. There are also two other navigation databases, the supplemental and the temporary. If the pilots need to use some information not in the permanent database, such as unpublished waypoint, they can insert it into the supplemental or temporary nav database through the CDU. Supplemental data is stored indefinitely unless removed by the crew. The temporary nav database is erased automatically on shutdown. There is also a performance database. This contains information on climb and cruise performance, thrust limits, maximum and minimum altitudes for various configurations, drag characteristics, and expected fuel flow. Maintenance personnel can refine this data by entry of correction factors for individual aircraft's drag and fuel flow characteristics, which are established from the aircraft's history. We said earlier that an FMS may be structured to have either one flight management computer or two. On those systems that have two, there are reversionary modes. Here is the system in its normal configuration. This is called dual mode. Each flight management computer produces independent calculations. The outputs are compared and checked for agreement. Minor differences are synchronized to one nominated FMC, usually the captain's. This results in both pilots' CDU displays being identical. However, if the cross-check shows a discrepancy above a predetermined value, the system changes to independent mode. This happens automatically in some systems and is selected by the crew in others. The synchronizing link between the two systems is broken. Now we have independent calculation and independent output. The pilot's displays may now conflict, and, if they do, it is up to the crew to choose which is the most likely to be correct. Finally, we may get a failure of one computer. In this case, the remaining one takes over both displays. This is called single mode. It is specifically a failure mode in which one FMC feeds both displays. Both pilots' displays will be identical. Let's summarize this lesson. The flight management system is designed to provide continuous automatic navigation, guidance and performance management. They vary from type to type, but they all contain a flight management computer, a control and display unit, 2 or possibly 3 inertial reference systems, an air data computer, radio navigation inputs, navigation and performance databases, and inputs of engine and fuel data. They simultaneously compute lateral navigation, or LNAV, and vertical navigation, or VNAV. The control and display units, or CDUs, consist of a display and a keypad, and are used during pre-flight to manually initialize the IRS and FMC with dispatch information, flight plan routing, zero fuel weight, and planned cruise altitude. In flight, they are used to control the FMC and display flight information, and to show alert and advisory messages. The navigation database consists of 2 AIRAC cycles. Unless at least one is current, the system will not function. The pilots cannot alter the permanent nav database. However, they can enter information into the supplemental and temporary memories. The performance database consists of climb, cruise and descent speeds, power setting and fuel flows. On systems where there are 2 FMCs, the normal operating mode is called dual mode. If there is a mismatch of information, the system reverts to independent mode. And if one FMC fails, the remaining computer feeds both displays in single mode. That completes this lesson. The next one will deal with equipment operation.